So, last class I was discussing about the two-way eccentricity. So, there are 4 cases. So, I have discussed 2 of them, the case 1 and case 2. Now, this class I will discuss other 2 cases, and then I will discuss few problems related to eccentric loading. So, now this is my case 1, when E L by L is greater than equal to 1 by 6 and E B by B is greater than equal to 1 by 6, and this is the case 2, when E L by L is less than 0.5 and E B by B is within 1 by 6 to 0. So, now the third case, this is case 3, when E L by L is less than 1 by 6 and E B by B is in between 0.5 to 0. Okay. So, E L by L is less than 0.6 and E B by B is less than in between 0.5 to 0. So, in such case, so this is the foundation, okay. So, this is the width of the foundation and this is the length of the foundation footing, and in such case the effective area is like this. Okay. So, this here loading is acting here, say this is my E L and this one is E B and Q is acting here, and this shaded area is the effective area. Okay. So, in this case, this is say B 2 and this one is B 1. Okay. And now, I can say again the area, effective area is half of B 1 plus B 2 into L, okay. And the effective length L dash is equal to L, because your this is the L, and B dash is equal to L dash by A dash by L dash. Okay. Now, this value of B 1 and B 2 will be obtained from this curve, okay, from this chart. Again, this is B 1 by B 1 B, this is B 2 B, and this is E B by B, this is E L by L. Okay. So, E L by L is less than 1 by 6. So, that is why E L by L is given up to 0.167, and this is E B by B is 0 to 0.5. So, this is 0 to 0.5. So, again if you go, this is the line, if you go above this line values, then you will find, or towards the right side, then you will get B 1 by B, and if you go towards the left side or below the values of this line, then you will get B 2 by B. So, okay, this is B 2 by B and this is B 1 by B, similar to the case 2. So, this way you will get B 2 and B 1 and L dash is equal to L, you will get the effective area by using this equation, and then you will get the B dash. So, now these L dash and these procedure will tell that how we can determine the effective area and A dash and B dash, or effective width or effective length. Now, this effective width or length or the effective area we have to use in our bearing capacity equation to determine the bearing capacity of the foundation, that I will discuss in example problem. Now, we have the last case. So, that is the case 4. So, in the case 4, the both the eccentricity is less than 1 by 6, EL by L is less than 1 by 6 and EB by B, that is also less than 1 by 6. Okay? So, this is 1 by 6 means 0.167. So, that is why this is drawn up to here 0.16, here also it is 0.16. Okay? So, now in such case the loading area, effective area of the foundation can be obtained as this is my L, this is B and this is the value. Okay? Or this is the area, or this is L2 and this is B2. Okay? And load is acting here, this is EL and this is EB, Q is acting here, this shaded line is the effective area. Okay. So, now how we will calculate the area of the or the effective area? Then the effective area A dash is equal to, because we can now divide it one rectangle and one trapezoidal. So, one rectangle whose length is B and width is L2. So, suppose now if I divide it into one rectangle and one triangle or one trapezoidal. So, this is the rectangle and this is the trapezoidal. Okay. Now, for the rectangle the area is B into L2 for the rectangle, and for the trapezoidal the area is half B plus, because this is B plus B2 into this length will be L minus L2. Okay. So, this way I can calculate the effective area, and then we know the A, L and B, then we have to determine the L2 and B2. So, how I will get the L2 and B2? So, this is the chart. So, you can see this is the value of EB by B, x axis is EB by B and these values are EL by L, and this y axis is B2 by B and L2 by L. Now, if I use the upward curve, that means these curves, the upward curves. Okay. So, then if I use these curves, then I will get B2 by B. Okay. So, if I use this curve, then I will get B2 by B. Now, if I use the downward curves, so if I use the downward curves, that means these curves, these downward values, okay, these charts or these curves, then I will get L2 by L. So, upward values, this upward curve will give me B2 by B and these downward curves will give me the value L2 by L. Okay. And then once I will get this L2 and B2, then I will get the effective area, and then I know this is the length. So, effective length will be equal to L and effective width will be A dash by L dash. Okay. So, this way we can determine the effective area, effective length or effective width for two-way eccentricity. Now, there is a question that when I talked about the one-way eccentricity, I have used one expression, that is my L dash is equal to L minus 2 into E L, and B dash is equal to B minus 2 into B L. So, now the question is that few researchers have suggested that you can use that expression also in these cases, but for my personal suggestion, that as those expressions you use for one-way eccentricity, and for two-way eccentricity you use these 4 cases that I have discussed. Okay. So, and that is my I prefer to use these things, because in those expressions is perfectly okay if we are using within the distance 1 by 6 EB or E by width or length is less than 1 by 6 or equal to less than 1 by 6, but here some cases it is more than that. So, I would prefer that you use one-way eccentricity to calculate those expressions to calculate effective width and effective length, but you use the procedure that is discussed for by four cases for two-way eccentricity, that you should use to calculate the effective width and length for two-way eccentricity. Okay. So, now the first problem that for eccentric loading, that a rectangular footing of size 3 cross 6 meter is placed at a depth of 1 meter in a homogeneous C5 soil. The water table is at a great depth. The unit weight of soil is 18 kilonewton per meter cube. Determine the net safe load. Net safe load, that means the net ultimate divided by the factor of safety. If C is equal to 100 kPa, phi equal to 20 degree, the load is vertical and acting at a distance of 0.3 meter from the center along the center line of the foundation in width direction. That means that EB by 0.3 meter. So, sometimes you will get this type of value will be given, that means load is itself acting on the on the foundation at a distance of say EB or EL from the center of the footing. Okay. But sometimes the moment will be given and we have to calculate the eccentricity. Then the moment will be given, the vertical load will be given. So, we have to calculate the eccentricity as I have discussed. So, in two ways you can do, either the eccentricity value EA, EB or EL will be directly given, or the mx or my will be given and the q value or the vertical load will be given. So, we have to calculate the EL or EB based on the value mx and my. Now, you use the Meyer-Hoff equation and assume general shear failure and as a factor of safety 3. So, now here in the solution we know that B is equal to 3 meter, L is equal to 6 meter, C is given 100 kilonewton meter square, phi is given 20 degree and EB is given 0.3 meter. Okay, and this is towards the width. So, that is why EB. So, now the Q net ultimate, I know the C N C, S C, D C, I C plus gamma D F, N Q, S Q, D Q, I Q plus half B dash, because here it is eccentric loading. So, and if you remember that I have discussed that if I use the Meyer-Hoff bearing capacity equation, then all the factors, those shape factors and dash factors, we have to use B dash and L dash, and for the third term of the bearing capacity equation you have to use B dash. So, that I am doing. So, B dash, gamma, N gamma, S gamma, D gamma, I gamma. So, and that is the net. So, gamma D F. Now, as the load is not inclined, so this I q, I c, I gamma all will be equal to 1. So, that is why I c equal to I q equal to I gamma is equal to 1. And but there is no data is available to check or to incorporate the compressibility effect. So, that is why the compressibility effect is not considered. So, as the data is not available, so you can consider the compressibility factors are also equal to 1. Okay. So, now you can see that for phi equal to 0, as it is a general shear failure is considered and no compressibility data are available. So, we are consider that all those factors are 1 and we consider the NC value is 14.8 and NQ value is 6.4 and N gamma value is 2.9 as for the Mayer of bearing capacity factors. Now, as per the Mayer of, this SC is 1 plus 0.2 tan square 45 degree plus phi by 2 into, now here instead of B I will use B dash divided by L dash. Okay. So, now what is B dash here? So, this is one way eccentricity as I mentioned. So, I will use the expression that I have given, that is B minus 2 EB. So, B is 3 meter, 2 into 0.3. So, this will be 2.4 meter, but there is no eccentricity along the length direction. So, L dash will be equal to L will be equal to 6 meter. So, now the B dash is 2.4 meter and in the L dash or is equal to 6 meter. So, that value if I put here 1 plus 0.2 tan square 45 degree plus 20 degree divided by 2 into 2.4 divided by 6. So, this is equal to 1.16. Now, similarly, the SQ and S gamma value, those are equal to 1 plus 0.1 tan square 45 degree plus phi by 2 into B dash by L dash. So, if I put those values, I will get the factor is 1.082. Okay. Similarly, I will get the DC, which is 1 plus 0.2 dF by B dash, okay, tan 45 degree plus phi by 2. So, now if I put 1 plus 0.2 dF is 1 meter, because the foundation is 1 meter below the ground surface, and then B dash is 2.4, then tan 45 degree plus 20 degree divided by 2. So, that is coming out to be 1.12. So, similarly, I can write dq and d gamma, which is 1 plus 0.1 df by b dash into tan 45 degree plus phi by 2. Okay. So, this value will if I put this value, I will get the correction factor 1.06. Again, I mentioned here water table is not considered. So, if the water table is here, then you have to consider the water table as per the procedure or water table effect as per the procedure that I have discussed in my previous lectures. So, now finally, the NQ U will be, C is 100, then this is 14.8 into 1.16, then DC is 1.12, then that IC is 1, then plus 18 into gamma W is 1 into 6.4 into SQ is 1.082, DQ is 1.06 plus 1 into 1 plus half into unit weight is 18 into, now it is B dash, B dash is 2.4, 2.4, then it is 2.9 is the bearing capacity factor, then the safe factor is 1.082, depth factor is 1.06, inclination factor is 1 minus 18 into 1. So, the final value is coming out to be 2108.8 kilonewton per meter square. Okay, 2108.8 kilonewton per meter square. So, now I can write that Q net safe will be equal to, because we have a factor of safety of 3. So, I can write that 2108.8 divided by 3. So, that will give me the value 703 kilonewton per meter square. So, 703 kilonewton per meter square. So, finally, the safe load that I can put on this foundation, that is the Q net safe into the effective area. So, okay, Q net safe is 703 into effective area is 2.4 into 6. Okay. So, 2.4 into 6, which is equal to 10123 kilonewton, or roughly 10 meganewton. So, the load that I can apply on the foundation is roughly equal to 10,000 kilonewton or 10 meganewton. But here I have considered the one way eccentricity along the width direction, and I have used the Mehrov equation. Okay. So, now next question that I will solve, that if I have a two-way eccentricity, then how I can solve or I can determine the bearing capacity. So, what I have considered, that I have taken a rectangular footing of size the same footing dimension, or more or less all the values are same, only in previous problem I have taken one way eccentricity, here I have taken the two way eccentricity. So, footing is 3 meter cross 6 meter, and it is a depth of foundation is 1 meter, and it is in the homogeneous soil. Water table is at a great depth, unit weight of the soil is 18 kilonewton per meter cube. To determine the net safe load when the C is 100 kPa and phi is equal to 20 degree, the load is vertical, but EL is equal to 1.2 meter and EB is 0.3 meter. So, now there is two way eccentricity, two eccentricity or E values are given. One is 1.2 meter towards the length direction, another is 0.3 meter towards the width direction. Use the Mehrov equation and assume general shear failure and a factor of safety of 3. Okay. So, now I will go to that case. So, that example, the similar type of problem, that my L equal to 6 meter, B equal to 3 meter and EL is equal to 1.2 meter and EB is equal to 0.3 meter. Okay. So, now EL by L is what? EL by L is 1.2 divided by 6, which is equal to 0.2 and which is less than 0.5. Okay. Remember that theoretically, as I mentioned, the maximum value of EL by L or EB by B can be 0.5, but it is very rare in the field that EB by B or EL by B is used greater than 0.2. So, maximum it can be taken or used in the field as 0.2. So, that means the eccentricity maximum used in the field is 20% of the length or width from the center, that means 0.2 times of length or width. So, it is rare that these values are taken greater than 0.2. So, that is why I have taken 0.2, and it is most of the cases it is limited to 0.167 or that less than 1 by 6. Most of the cases it is limited to 0.167 or within the 1 by 6 or 0.167 value, but rarely it is beyond 0.2. So, remember that. So, but I have discussed, but theoretically you can go up to 0.5, but actually in the field it is not used it as up to 0.5. It is generally it is limited to within 0.167 or it can go around 0.2 and so not more than that. So, so that means this is my 0.5, and then EB by B is equal to 0.3 divided by 3, it is 0.1. So, which case it will be? So, this case is that EL. So, this case which is EL by L is less than 0.5. So, that means my EL by L is less than 0.5 and EB by B is within 1 by 6, means I can say 0.167 to 0. So, that means it is case 2 that I have discussed in among those 4 cases. So, this is case 2. So, this is the chart for the case 2. So, let me calculate the effective area. So, effective area is for the case 2 is half L 1 plus L 2 into B. Okay. Now, as the EL by L is 0.2 and EB by B is 0.1. So, let us do that. EL by L is 0.2, this is the value, and EB by B is 0.1. So, that means this is the 0.1, this is the 0.1, here also this is 0.1. So, as I mentioned, if I go above this line or towards the right side, then I will get the L1 by L, and towards the left I will get the L2 by L. So, let us first calculate the L1. So, this is my 0.2 line. So, this will go to this line. So, this is the value. Okay. So, as I mentioned, this is 0.9 and this is, so this will be 0.88. So, from the chart I will get that L1 by L, because this will give you the L1 by L, that is equal to 0.88, and for the L2 by L, so this is 0.1. So, this direction L2 by L, so this is the value which is 0.22. So, from the figure this L2 by L is 0.22 corresponding to EL by L is equal to 0.2 and EB by B is equal to 0.1. So, I will get the L1 and L2. So, my L1 value will be equal to 0.88 into 6, L is equal to 6. So, 0.88 into 6, this is 5.28 meter, and L2 value is equal to 0.22 into 6. So, this will be 1.32 meter. So, as I mentioned, the longer of this L1 and L2 will be the L dash. So, the L dash value is equal to 5.28. Okay. So, L dash equal to 5.28. Now, what is the A dash value? A dash value is half plus 5 into 5.28 plus 1.32 into 3. So, that is equal to 9.9 meter square. So, this is the effective area. So, the effective width will be the A dash divided by L dash, which is 9.9 divided by 5.28. So, that is equal to 1.875 meter. So, now I have already calculated that what is the L dash value. L dash value is 5.28 meter and B dash value is 1.875 meter. So, now I have calculated the L dash and B dash and the effective area. So, next class I will use this effective length and width, and then I will put these values to calculate the bearing capacity factors and or the correction factors, and then the bearing capacity of the foundation by using the Mayer of bearing capacity equation. So, I will solve the remaining part of this problem in the next class. Thank you.